Homework 3.2, Polynomial Functions, video number 1. Homework due Wednesday, May 27th, 2020 at 11:59 p.m. There are no specific homework questions that correlate to the material in this video. This video serves to transition from the previous series about quadratic functions into the current series of videos about polynomial functions. Speaking of previous series in quadratic functions, in homework 3.1 we discussed quadratic functions, what they looked like, what their graphs looked like, parabolas, whether they opened up or down, we found the vertex, we found the axis of symmetry, we found some intercepts and all that jazz. Well, the problem with quadratic functions is by definition the highest power they contain is x to the second power. Prior to this test, back in sections or homework 2.3 and 2.4, we discussed linear functions, which by definition have a highest power of 1. So it's natural to say if we've discussed polynomial functions whose highest power is 1, their graphs are lines, and polynomial functions whose highest power is 2, their graphs are parabolas. What happens if we make the highest power 3, or 4, or 5, or 6? Now, we could technically do a whole series of videos in a whole homework section over just third degree polynomials, and then do it again for fourth degree, and then do it again for fifth degree and beyond, and stop it at some point. But once you go from quadratic and beyond, there are less and less specific techniques for dealing with polynomial functions, and we start discussing them more generally. For example, for quadratic functions, we have some very specific tools that we can use. We can use the quadratic formula to find the x-intercepts. We can use the formula for the vertex to locate the vertex. We can look at the leading coefficient and determine instantly if the parabola opens up or opens down. But once you go beyond quadratic and go to third degree, x to the third power, x to the fourth power, we lose a lot of those specific tools. So we have to speak a little bit more in generalities. So to make this transition, what I would like to do is categorize the things that we know about quadratic functions and kind of introduce you to how they're going to transition into the discussion of polynomial functions in general, functions whose highest power has no limit. So for example, when we talked about quadratic functions, one of the forms was f of x equals ax squared plus bx plus c. There was another form called standard form that contained information about the vertex, but most of them look like this. Well, how can we generalize what a polynomial function looks like? Because a polynomial function doesn't have a cap on how big the largest power can be, how large the degree can be. And as I use some of these words, I need to start defining them. The word degree means the highest power in a polynomial function. Technically, it's just a word for polynomial, but since we're talking about functions, we'll usually say polynomial function. So for quadratic, by definition, its degree is 2, and so it's really easy to represent generically. At most, this is going to have 3 terms, an x squared, an x, and a constant. And we can represent their coefficients generically too with just a, b, and c. But when it comes to representing a general polynomial with some degree that we don't know, how are we going to write that? Well, when we need to represent something we don't have a specific value for, that's a good time for a variable. So if we're going to start off this polynomial with some highest power, we need a letter to represent that highest power. We're going to use the letter n. And we need something to represent the coefficient. Now over here we just use a because it was the first letter of the alphabet, but we run into a problem if we try to replicate that here. Specifically, when I get to the next term, if it's written in standard form, general form, would be the next highest power below this one. Well, how do you represent the next highest power below n? In other words, how do you represent the number 1 before n? And the answer is you represent it as n minus 1. So for example, if this were a 5, then this would be a 4. So x to the 5th, x to the 4th. But what are we going to represent this coefficient with? Could we use a b? Well, we could, but the problem with that is I don't know how many terms there are over here, because I don't know what this degree is. It's generic. In theory, the degree could be larger than 26, and if it were, then we would run out of letters of the alphabet to use as coefficients. We could resort to Greek letters or other alphabets, but let's not go there. So instead of calling the coefficients a, b, c until it ends at some unknown point, let's recycle the variable. In other words, let's recycle the a by subscripting it. Now the natural thing to do would be to call it a subscripted with the 1, but I want something a little bit more meaningful than that. I'm going to subscript the a with a number that matches the power on the x. So for example, if this is x to the n power, then I'm going to call this leading coefficient a sub n, meaning the coefficient in front of x to the nth power. And if I follow suit, what do you think I'm going to call this coefficient? Well, if I'm subscripting them with a number that matches the power on the x, then this would be a sub n minus 1. Now, how long will this go? Well, it goes until you run out of x's, until you get to a constant term. Since we really don't know how many terms this is, we're going to set up some ellipses here to represent and so on, and then just show you how it ends. Now, a polynomial function in general will end with an x term and a constant term. We'll write the constant term in a moment. If I'm going to be consistent with the way I generically represent the coefficients, I need to use an a subscripted with a number that matches this power. Since the implied power is 1, we'll call it a1. And as far as the coefficient, the constant at the end, if I'm following suit, I'm going to call it a subscripted with a number that says how many x's are on it. But there are no x's on it, so we'll call it a sub 0. And again, don't let this mess with your head. This is just a generic representation of a polynomial function. Some power of x with some number in front, plus, it could be minus if this were negative, the next highest power of x with a coefficient in front of it, and then you work your way all the way down until you get to 1x and then no x's. A little bit of vocabulary before we move forward. We've already defined degree as the highest power in a polynomial, so this would be called an nth degree polynomial. The leading coefficient, which is a phrase that I've used quite a bit, but I'm not sure if I've ever officially defined it. The leading coefficient is the coefficient of the term with the highest power. Coefficient of the term with the highest power. In other words, whichever term is determining the degree, its coefficient is called the leading coefficient. It's called that because it usually leads off the polynomial if your powers are in order from highest to lowest. So it's a little tricky to represent it generically, but basically we're saying start with any power you want, any coefficient, keep going down until you run out of x's and have a constant term at the end. Now, what about the graphs? Well, the graphs of quadratic functions are predictable. They're parabolas, so they look like that or they look like that. But with a polynomial, well, let's just put it this way. The larger the power, the more the graph can turn. So these graphs can start high or low, turn at an unpredictable number of times, and end up either high or low. Now, I don't want to mislead you into thinking that it always starts out pointing down and always ends pointing up. We'll discuss what the ends can do here in a moment, but we have no definitive shape of a polynomial function because the more x's and the more powers, the more it can twist and turn. As far as symmetries, we know that a parabola has an axis of symmetry. But when you have graphs that twist and turn an unpredictable, it's actually a predictable number of times, and you don't know how high or low it goes before it turns, we're probably not going to have any symmetries. However, we can still talk about being an odd function, which means you have origin symmetry, or an even function, which means you have y-axis symmetry. So it is possible to track down some symmetries for polynomial functions. When we run across it, I'll remind you how to determine if a function is odd or even, and hence its graph has origin symmetry or y-axis symmetry. As far as the number of turns, a parabola will turn one time. It'll turn at its vertex. But there is a way to predict the number of turns a polynomial function's graph will make. At most, there will be n minus 1 turns. So whatever the degree is, if you subtract 1, that's the most number of times the graph can turn. For example, if you have a 4th degree polynomial function, then it can turn at most 3 times. I say at most because it can turn fewer times, but it has a maximum number of times it can turn. As far as the ends go, for a quadratic function, it's pretty predictable. Either both ends rise, meaning that they both point up, or both ends fall, meaning that they both point down. But when you have a generic polynomial function, there's no guarantee that they'll match, that they'll both point in the same direction. So more generically, we can say the left end falls or rises. Falls meaning it points down, rises meaning it points up. And we can say the right ends. Left end falls or rises, right end falls or rises. And there's only 4 combinations. Either they both rise, they both fall, or the left rises and the right falls, or vice versa. So there's only 4 combinations, and we'll figure out in advance how to predict what the ends will do. The story for the y-intercept is the same. For a quadratic function, you just substitute 0, but the truth is you do that for any function. So that's consistent. Stick in 0 to find the y-intercept. And for the x-intercepts, we have to solve the function equal to 0, which is the same thing we do here. Solve f of x equals 0. But I'll go ahead and foreshadow, but there's more. There's more to the discussion than just saying, I know where it crosses the x-axis, as you'll see here in a moment. So as we transition into polynomial functions, we'll be kind of analyzing the same characteristics of graphs that we did for quadratic functions, but on a much, much more generic scale.